So I'm getting ready 8. We're going to start here looking at some graphs of quadratic equations, so some parabolas. All right, so the different parts of the direction say we need to make a point on the vertex and draw a dotted line for the line of symmetry. Okay, so we'll make a point at the vertex, which is either the lowest or highest point on the graph, and a dashed line through for the line of symmetry. All right, we are then to label the coordinates of the vertex and tell whether it's a maximum or a minimum. So this vertex was at 0, 0, and that point represented a minimum since this was a graph open up. And lastly, the fifth part, write an equation for that line of symmetry. Now remember, the parabolas that we are graphing this year in algebra are always either open up or open down. Therefore, the line of symmetry is always vertical, and it's always x equals, and then just the first number of our vertex. So x equals 0 in this case. Okay. Number 2 here, put a dot on the vertex, dotted line for the line of symmetry. Label the vertex, so that's 4, 0. Again, the parabola is open up, so this is once again a minimum. And the equation for that axis of symmetry, this time is x equals, and it's again the first number of the vertex, x equals 4. Number 3, point on the vertex, dashed line for line of symmetry. Coordinates of the vertex, this time -1, -2. Parabola, for a third time in a row, is open up, so we have a minimum. And then the equation for the line of symmetry is x equals, this time it's going through the -1, x equals -1. Number 4, point on the vertex, dashed line for line of symmetry. Label the coordinates, so it's -3, 5. And then equation for the line of symmetry is x equals, the x coordinate from the vertex, -3. Number 5, oh, I'm sorry, we forgot one thing. In number 4, we forgot to identify that the vertex is a maximum. This time, the parabola is open down, so that vertex is at the top rather than at the bottom. Okay, so number 5, dot on the vertex, dash line for the line of symmetry. Coordinates are 1, 3, which this time again is a maximum because it is at the top of the parabola. And my equation for the line of symmetry is x equals, the x coordinate here, 1. One more. Our last one, we have a point on the vertex. Now this time, the vertex is somewhere between 1 and 2, or at least the x coordinate of it. So we identify it here, draw in that line of symmetry. But when we go to identify these coordinates, you're kind of making a guess at this point. It looks like it's about 1.5, and then y coordinate is -3. It is definitely a minimum since it's at the bottom of the parabola. And then your line of symmetry, again, you are making an estimate for this x coordinate, so that same number should be used to say it's x equals, for me, 1.5. If you used a different estimate than 1.5, your line of symmetry should match that. Now, we are going to come up with a way to identify that in a more certain way here in a moment. So questions 7 and 8, let me get these out of here. Questions 7 and 8, I wanted to use the graphs that we just looked at here. So I'm bringing those questions into this page. What connection exists between the coordinates of the vertex and the equation of the line of symmetry? Well, we said that over and over as we did these. The x coordinate of the vertex is the same number we use when we write the equation for the line of symmetry. So if vertex is, let's say, AB, then the line of symmetry is and it's always x equals, for our open up and open down parabolas, x equals the A. The x coordinate here matches the constant in our equation. Now, here's where we're going to do a little bit better job with number 6. This says, look back at that. Try to find a way to identify the exact value of those coordinates, and then go back and test that from 1 through 5. Now, I don't know if you would have found this on your own, but I'm going to show you exactly how to identify that. Because of the symmetry of a parabola, the vertex always resides, it's always found exactly in the middle of the graph. Now that also means, though, it's exactly halfway between these two x-intercepts. So if this x-intercept is at -2, and this one is at 5, if I could locate the point exactly halfway between -2 and 5, that's going to identify the line of symmetry and therefore the x coordinate of that vertex. So halfway between -2 and 5, another way to say that is I just want their mean or their average. So -2 plus 5, chop that in half. -2 plus 5 is 3. Divide that by 2, and there's our 1.5 that I estimated earlier. Okay, so our conjecture here would be that the x coordinate of the vertex is the mean or the average of the x-intercepts. Okay. Again, that's assuming we have two x-intercepts. Sometimes we have none or one. Right. If we go back and verify that, we would have to look just at the ones that have two x-intercepts. So on number 3 here, now this looks like it's maybe 1 1/3 and -2 1/3. So again, we're estimating the x-intercepts there. -2 1/3 plus 1 1/3 would be -1. I'm sorry, that's 1/3 and -2 1/3. So -2 1/3 plus 1/3 is -2. Divide that in half is -1. It works there. This looks like about -2/3 and -5 1/3. Maybe that's -3/4. I'm having a hard time estimating that. You know what? We're going to edit out this whole nonsense about checking 1 through 5. So edit this out. Okay, number 9. How many x-intercepts can a parabola have? Well, if we kind of just sketched in the different possibilities for parabolas over here, if I had one that's open up, it could rest up here, so it doesn't have any x-intercepts. It could come down, bump the x-axis, and back up, so it has exactly 1. Or it could come down, hit the x-axis, then when it returns up, hit it again. So it could have 0, 1, or 2. Now, I could also look at ones that open down the same way. I could have one that stays all below the x-axis, one that just bumps the x-axis, or that hits it twice. So it looks like the number of x-intercepts can either be 0, 1, or 2. There's no other, you cannot have 3 or more x-intercepts. So 0, 1, or 2. We want to sketch a parabola over here on this graph that has no x-intercepts and then tell what it was that made that happen. Well, we already drew a couple of those, so you could draw one either above the x-axis or below. But let's say I identify my vertex here, and I want this to be like my standard opening or standard width of the parabola. What is it that made that happen? Well, the first thing is it has to be all above or all below the x-axis. But what is it that makes that happen? Well, it's a translation. It needs to translate above or below the x-axis. Okay. For example, if we were keeping it simple, we could have y equals x squared plus 2. Or if we had one open down, y equals negative x squared minus 2. Right? So it would have to translate above if it's open up, or below if it's open down. All right, we're going to look at some of these algebra tile models and choose which one matches each expression. Okay. So I don't know if you want to look at the expression, try to find the model, or look at the model, match it up. I think I work better looking at the model first. So this one has just all the large x squared tiles. So the area of this one is x squared. This is x by x for x squared. So there are no single little unit tiles. There are no long, skinny x tiles, only x squared. And I have 4 of them exactly. So number 14, 4x squared, is A. For B here, I have one of the large blue squares, x by x, so that's an x squared tile. I have 1, 2, 3, 4, and then 5, 6, 7, 8 of these x tiles. And then we have 16 of the little apricot unit tiles. Okay? So what causes that to happen? Well, we have a square overall. Each side length is x plus 4 units. This is x plus 4. So the area of that entire thing would be x plus 4 times x plus 4, or in other words, it's number 12 here, quantity x plus 4 squared. C, I have the one large x squared tile, and then 4 little unit tiles. No long, skinny green ones, no x areas. And it's not overall a square as the other 3 shapes are. This is the only one that is not a square. So it is number 11. It is just an x squared with 4 units added onto it. And lastly, D must be number 13, but let's see why. This is that we have 4 of the the large x by x tiles. So each one of these is x squared. Each side of this overall big square, each side is 4x. So the area of the entire square would be 4x times 4x, or another way to write that, quantity 4x squared. So 13 is D. Next, we're going to look at a table of, a table of values. We're going to compare it back to the table of values for the parent function. So that's given to us there above the directions for 15 to 18. Hopefully that's one you've kind of got a feel for and you've practically memorized at this point. So we're going to compare each new table to that one so we can decide what had to change, what translation had to occur. We're going to identify which way it moved, which part of the equation shows that move, and write the new equation. Okay? Now remember, the parent function is f of x equals x squared, but our vertex form, we would say, is f of x equals a x minus h squared plus k. We know the a out here controls our dilation and whether it's open up or down. The h here controls our horizontal motion, left or right, and k, up and down. So, trying to think, you would probably start this, I suppose, since you have a table of values, by graphing. So, -3, 2, okay, so once we get those, 7 points plotted, we could go ahead and sketch in our parabola. Now, how does this one compare to the parent graph? And we could be looking at either the graphs or the tables or a combination of both. And what we see is it is just shifted down, vertically down 7 units. That vertex goes from being located at 0, 0 to 0, -7, right? And each of the y values is just 7 less than what we saw from the parent graph. So what makes that happen in an equation? It's the k. The k controls vertical motion. So our equation, just x squared minus the 7, the vertical translation down. So it moved down 7, and the part of the equation that showed that move was the k. I've got y values up to 11, and those won't fit on the grid as we see it here. So I'm going to need to at least make my y scale 2's. I can keep the x scale counting by 1's. Okay, sketch in the parabola. Now, if you were really comparing this to the graph that you see above on your paper, it's going to look wider, like there was a dilation. That is because we changed the scale. So you always want to watch out for that and be aware of it. If we look at just the tables, though, each of the y values here, as we compare them to the parent table above, is just 2 above. Instead of 0, 0, we see 0, 2. Instead of 1, 1, we see 1, 3. Instead of 2, 4, we see 2, 6. So each one is just, we've added 2 to the y value. So this graph really only moved up 2, right? That, just like we did in 15, that is controlled by the k value. So our equation is x squared plus 2. All right, and the 9s will be just 2, 4, 6, 8. Yeah, will be just off the grid. I think I can go ahead and just plot them right above the graph, though, and not really bother you too badly. This one, it looks like we moved left 1. Now, in order to check for that dilation, remember, all we really need to do is go to the side 1 unit from the vertex. If we go to the side each way, 1 unit, and see, okay, what's the vertical change, or how far away are those next 2 points? To the side 1, we go up 1. To the side 1, we go up 1. That's exactly the same, I don't know, dimensions or same width as the parent one. So that tells us there was no dilation, okay? Again, what we're looking at here is from the vertex, and here's your vertex this time. When we go to the side 1 each way, this goes up 1, that goes up 1. So we have not dilated this. All we have done was moved it left 1 unit. Now, what part of the equation shows that? This time it's the h. Okay, this is inside the parentheses. So we need parentheses. It's x squared. There won't be an a value, or at least it remains 1. There won't be a k value because we did not shift vertically. To move left 1, we actually have to change this since it's minus the -1. That becomes x plus 1. So really it turns out that the sign inside the parentheses always is opposite of the direction you move. We moved left, our sign is positive. And 18. These ones, again, we're going to have to get up to 9, so that'll be one space a little above the grid. We can live with that. So 0, 9. All right, so we sketched in our parabola at number 18. It looks like it definitely moved to the side 3. Okay, so this one moved to the right 3. It did not have a vertical translation, but we do need to check once again for a dilation. Well, again, we can look in the graph, and when we moved right 1 box and left 1 box, the next point I see is just up 1. Or looking in our table here, as we moved left to right 1 from the vertex 3, 0, these values just went up 1. That means it matches the width, the openness of the parent graph. It has not been dilated. So we only moved right 3. That's controlled by the H. And like we did in number 17, we need to put that in the parentheses, and it must be opposite the direction we move. Since we moved right 3, we're going to say minus 3.